remember what we're doing now is to experimentally determining the rate law. That's the goal of this module, okay? So what is meant by the rate law? That's the relationship between the rate and the concentration of reactants, and then finding the values of K and the orders of the reaction. That's it. Anyway, so that's what we're doing. Now, to do this, when we go to the lab, we are going to be collecting data. Okay. So what data we collect? We'll be collecting time and concentrations. Okay. That's all we do when we go to the lab. Okay. So once we collect the time and concentration data, all we need to do is three things. I'm going to get to that in a second. Okay. But I'm going to show you the possibilities first. Let me see if I can do it. Okay, coming up. There you go. All right. So when it comes to the rate laws, we know there are only three possibilities that we are working with. Okay, so we already did this the other day, but I'll redo anyway because I hope that you're gonna have something like this in your one-page notes as well, a smaller version of this. Okay, so let's do this together. Okay, so rate laws. Let's think about a reaction. So reactants going to products is our reaction. Okay. Now, what are the possibilities? Even if you go to the lab, what are the possibilities? It can be zeroth order. It can be zeroth order, meaning rate law would look like rate is equal to K. That's it. Okay. If you want to do a little bit more, you can write reactant to the reactant concentration to the power of 0. It's the same thing. Okay. Or it could be first order. If it is first order, rate is equal to rate constant times reactant concentration to the power of 1. Okay. And then it could be second order. Please, can you pay attention for a second, please? Can you pay attention for a second? Okay. So rate should be equal to rate constant times reactant concentration to the power of 2. Okay. Those are the only three orders we are dealing with. Okay. Now, the issue is, okay, if you, let's do everything together now. Okay. So if you plot rate versus reactant concentration for a first or a zeroth order reaction, okay, the rate does not depend on the concentration of the reactant concentration. As a result of that, we are going to get a straight line. If I can, okay, we're going to get something like this. Okay, why? The rate does not depend on the reactant concentration because it's zeroth order. Okay, whatever the concentration of R is, okay, reactant is, the rate is always equal to K. That's the idea here. Okay, that's why we're going to see a straight line like that. Okay, and then for a first order reaction, okay, for a first order reaction, the rate of the reaction is directly proportional to the reactant concentration. Okay, as a result of that, you're going to get a linear graph like that. The rate is going to increase when you increase the reactant concentration. Okay, and then for the second order reactions, okay, rate is highly dependent on the reactant concentration. Okay, as a result of that, when you increase the reactant concentration, the rate is going to increase a lot, or exponential kind of relationship here. Okay, so these are the rate versus reactant concentration graphs. Okay, now the other thing is we can think about how the reactant concentration changes with time. Okay, so if you do that, I'm going to use small graphs now. Okay, you can do the same thing. So let's think about how the reactant concentration changes with time for a zeroth order reaction. We already know this. We know the rate of the reaction does not depend on the reactant concentration. So whatever the case, you're going to see it's going to have the same slope. So it's going to have a linear graph like that. Okay. And then we also know, we'll not talk about that later. I mean, we can talk about it later. The slope of this graph is equal to negative k. We'll talk about that a little bit later. I'm going to redraw this graph. And then when it comes to first order reactions, okay, time, reactant concentrations, okay, what's going to happen is, well, with time, the reactant concentration goes down. As a result of that, the rate of the reaction decreases as well until it reaches the equilibrium. Okay, so the slope, we know the slope or the derivative. Let's call the slope. Slope of this graph is the rate of the reaction. You see the slope is decreasing with time, meaning the rate of the reaction decreases with time. Okay, why this is the case? When the reactant concentration goes down, the rate decreases. That's the idea here. Okay, that's why this is happening like that. And then when it comes to reactant concentration versus time, the same graph for the second order reaction, okay, it's going to be more dependent on the reactant now. So as a result of that, it's going to be more steeper. Something like that. Now, I cannot distinguish between, you see that, I cannot distinguish between first and second. Okay, I know that you had the same problem, right? So therefore, what we did was we relied on integrated rate laws. What we did was we took the rate laws, okay, over here, and we integrated them. And then for the 0th order, I'm trying to do it in my head while I'm doing this here. For the 0th order, we saw that the reactant concentration at time t was equal to minus or negative k t plus initial reactant concentration. Okay. So for the first order reaction, what we did was when we integrated it, we have natural log of reactant concentration, and that was equal to negative k t plus natural log of initial concentration of RO. John? Yes? Yeah. Did I do anything wrong? Okay, thank you. All right. Yeah, it's good that you're checking my work. All right. And then when it comes to the second order reactions, if you plot, so we saw that when we integrate, we have 1 over reactant concentration, and that is equal to not negative k, but k times or rate constant times time plus 1 over R naught. Okay. So these are the integrated rate laws. So we can write them. These are my integrated rate laws. Okay. So one of the questions I was getting was, I mean, when I inquire, so I mean, I have trouble like deciding which equation to use. Okay. So if it is 0th order, here's the rate law. Let me write that too. Here's the rate law. Okay. And here's the integrated rate law. And if it is first order, here's the rate law. Okay. And here's the integrated rate law. If it is second order, here's the rate law. And here's the integrated rate law. Okay. So what this means is this. I'm going to draw 3 other graphs now again. If you plot reactant concentration versus time for a 0th order reaction, you're going to get a linear graph like that. And the slope of that graph, okay, so the slope of that graph, is equal to negative k. Okay. And then when it comes to first order reactions, what you're going to do is you're going to plot not reactant concentration versus time, but natural log of reactant concentration. So natural log of reactant concentration versus time. And if you do that, again, you're going to get a linear graph. Okay. And the slope is again equal to negative k. This is the lowercase k for the rate constant. Okay. And then when it comes to, by the way, all of these are lowercase case, okay, because we are talking about the rate constant. Anything related to rate is rate constant, okay, and then that k is denoted as a lowercase k. Now, lastly, for the second order reactions, okay, if you plot 1 over reactant concentration as a function of time, then you are going to get a linear graph, but this time we're going to have a positive slope. You see that we have a positive k value here, a positive slope here based on our derived equation. Therefore, the slope is directly equal to rate constant. Okay. So far, this is what we have discussed. Okay, this is this half a page or maybe 2/3 of a page recapitulates everything that we have discussed so far when it comes to graphs. All right, I'll give you 30 seconds to think about this, and then I'll take any questions you might have about this. Anything? Isha. I'm going to talk a little bit more. It will be more clear in a bit. All right. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions? Yes. Really? Can I have the microphone with? Okay. Thank you, Aiden. Really go ahead.
So in that last one, the concentration of the reaction over
On
time.
over concentration?
Yeah.
Uh-huh.
Are the zeroth and the first exactly the same for that last row we did?
No, in zeroth, we plot concentration versus time.
Okay.
In first, we plot natural log of concentration versus time.
Okay. I meant on the graph part. It's like the slope equals negative k.
Yeah. Slope would not be exactly the same. They will have different units.
Okay.
Yeah.
Okay.
Yeah, we'll do them. Uh-huh. All right. What other questions, concerns, comments do we have? Lauren, anything? Okay. Yeah. Huh? All right. Now, here's the plan now. Because we know how zeroth, first, and second order graphs look like, okay, we can come up with a plan. All right. Here's the strategy. So we go to the lab. We go to the lab and we collect data. Right? What data do we collect? We are going to collect concentration and time data. Okay, we're going to collect concentration and time data. So that's the first thing you do when you go to the lab. All right, you measure time and then the concentration at those times. That's it. Okay, and then what we're going to do is we are going to plot concentration versus time, natural log of concentration versus time, and 1 over concentration versus time, and see which one is linear. We're going to plot all 3 graphs and see which one is linear. Okay. So if concentration versus time graph was linear, then it is 0th order. If natural log of concentration versus time was linear, then it's first order. And if 1 over concentration versus time was linear, then it is second order. That's it. So we just determine the order with respect to that reactant. We're done with that. Okay. And then from the linear graph, we can determine the slope. Okay. And the slope tells us the rate constant for the reaction. Voila, that's all we need. We are done. We go home and sleep. Yeah, that's it. That's all we do. All right. Any questions, concerns, comments? It's very simple, okay? The kinetic experiment is fun. I have taught this for many years when I was a graduate student, okay? So it's a fun experiment, okay? If you know what's going on. If you're measuring absorbance, okay, you can either use absorbance directly in when you plot the concentration versus time, or you can convert that to concentration first using the Beer-Lambert law and then plot them. It's really fun. And it's fast as well. All right. Do we have any questions, concerns, comments about the strategy?
There's a question over here.
Thank you.
Is this
What's your name? Oh, Queen.
sorry, Aoife?
Aoife, I'm sorry.
All good.
Is this just for lab, or are we gonna have to be doing this on like the test or
Oh no,
anything?
oh yeah, you're gonna do this on the test. Yes, absolutely. We're gonna have so much fun in the test.
Okay.
Because only difference is you won't be collecting data. I'm gonna give you the data. You're gonna plot these graphs.
Okay,
Yeah.
so we need to know like the whole graphing calculator thing.
Yes. I posted 2 videos so far. I think that should, that should take care of that. Yeah, it
Okay,
doesn't take
thanks.
time. Once you know how to do it. All right. Now let's have some fun. Okay. Now you know what's gonna happen. Imagine that we went to the lab and collected these data. All right. You went to the lab and collected data. This is in years, but that's okay. It can be years, seconds, minutes, hours. I don't care. Okay. It's just time. All right. Now, what I want you to do is I want you to use this data and determine the order with respect to the reactant, which is alanine. ALA means alanine. Okay. And then the value for the rate constant. Go ahead. I'll give you 5 minutes in your groups. Take your calculators out from your holsters. Okay. Then have fun with it.
Okay, which is K is the
Right, here are our responses. Yeah, this is where we stand, okay? All right. So now, can I please have your attention again? I'll reopen the question as well, but I already reopened it. Maybe I should close. But anyway, but I need your attention for a second, okay? So what we want to do is we need 2 more columns here. One of them is Ln reactant concentration. The other one is 1 over reactant concentration. That's it, okay? And then to get the natural log of ALA reactant concentration, you type equal sign, okay? And then type Ln, double click on that and click on the number, the cell with that number, and close the parentheses and hit enter. And then go back to that cell and double click on this small square, and it's going to populate the entire column. Okay. And for 1 over concentration, equal sign 1 over concentration. And then go back to that. And then, double click on the small square. It's going to populate that. Now it's easy. All right. Now we're done. Okay. So now we select the data. So I'm going to first select I'm going to first plot concentration versus time. Okay, select those data. Okay, just select them like that. Go to insert, scatter plot, choose this plot. Okay, and then it's going to plot the data for you. And then left click on one of the data points, and then right click, add trend line, and it's going to give you these options. I'm going to make it display equation on chart and display R squared value, which is going to give us an idea about how correlated our data are. And then that's all we need. Give me a second. All right. So this is my 0th order plot. All right, here we go. This is better. Okay. Now this is the 0th order plot, but if you want the 1st order plot, you want to select natural log of concentration. So what I'm going to do is I'm going to go to my blue box over here, the concentration data box over here. And I'm going to simply drag that. Let me see, Control C. Okay. Simply drag that box to the Ln concentrations. Okay. You see that it's going to give us the equation for the 1st order plot. Now this is my 1st order. Right. So for the 1st order plot, the R squared value is 1, meaning your data are correlated nicely in the 1st order plot. So I'm going to go with this. But for the sake of looking at it, I want to see the 2nd order plot as well. Here's the 2nd order plot. The R squared value is not 1, it's 0.99. So the closest one to R square to 1 was the 1st order plot. Therefore, I'm going to say my order with respect to alanine is 1st order because R squared is closest to 1 there. You cannot get better than that. Okay. So this should be a 1st order reaction with respect to alanine. That's how we determine the order. Right. That's it. That's all you do in the lab as well. In the lab, you will have to plot this like, three times. So what you can do is you can, I mean, there are different ways of doing that. You can, I think, copy another one to the end, create a copy, and then have the second order plot here or something like that. Okay, so this is the first order. If you want the second order in the second tab, you just do that. That's it. So you have first order here. This is first. This is second. Okay. And you can do the zeroth as well, the same way. Anyway, so this is your plot. All right. What questions, concerns, comments do we have about this? Anything? Any questions, concerns, comments? How's it going? Not bad. Not bad. Lauren, Max, any questions? Yeah. This is all you do. This is it. Okay. Yeah. You plot the data and see which one is linear, and the linear graph tells you the order with respect to that reactant. That's it. Done. Okay. It's a fun lab, by the way. All right. Now, we have that. I'm going to leave that here. Okay. Reese, did I clarify your question? Okay, perfect. Let's do this. By the way, so my plan was to complete at least 90% of what you're going to see on the exam 2B by today. Apparently, I'm going to be completing close to 95%, which is great. Okay. So the idea was to give you more time to practice with your calculator and then, play with this data. So you should be able to do that now. And also, even though Unit 5 Module 4 homework is due after exam 2B, I highly recommend that you do at least one attempt tonight before exam 2A, because I'm going to include a question or two from homework Unit 5 Module 4 on your exam 2A. Okay. So right now we can do it. Just one attempt. All right. And also, I think some of you did not realize it. So for your reading assignment that was due last night, at 11:59 p.m., I posted the answer key with my explanations like around noon yesterday. So if you had any issues there, please go and watch that video. It explains all the answers to the questions. Yeah. First of all,
Well, you
okay,
have to graph.
option A cannot be your answer, right? So we know the slope of this graph. Okay, what you did was you plotted, I cannot draw here, natural log of
like the x value is
concentration as a function of
column you're going to change. So you're going to try
time.
concentration of colony and see if that's linear. If it's not, then move on into the ln of the concentration.
Okay.
That's linear.
So, and then you got a graph like this.
Concentration of colony. That's
Okay. So people who selected option A as the answer, pay attention to this. Okay. Our slope of the graph is negative. Therefore, you need to have a negative sign in front of, this value over here. Okay. For that, because of the lack of that, option A is incorrect. Okay. And then I don't know what's going on with B here. It doesn't see, anyway. So it should be LNA. So I'm going to get rid of that.
okay.
And then natural log of initial concentration should be 0 because ln of 1 is 0. Therefore, the correct answer must be option C. I'm going to get rid of this as well.
That one. Yeah.
Okay. And how do we know that? One more time. We already did that, right? So we have that information in our Excel graph over here. This is the answer. Okay. All right. All right. What questions, concerns, comments do we have? So we know our slope is negative. Here's my slope. It's a negative slope. Okay. And the slope is equal to negative rate constant. Okay. Therefore, what's the rate constant for this reaction? So rate constant must be negative slope, right? So according to our answers, let me see. Our slope is negative 0.0693. Therefore, our rate constant must be negative 0.0693. Okay. But this is just the value. You see that we should have per time here, right? So it should be per time. Let's say t minus 1. Yeah, let's get rid of that for the moment. Let's concentrate on the value. So it should be a positive value. So it should be 0.0693. Okay. So this should be per year based on the data given. All right. What other questions, concerns, comments do we have? Anything? Kayla, did that answer? Okay. Yeah. Huh? What other questions, concerns, comments we have at the moment? Anything? Okay. Now I'm going to show you one other thing. This is going to show up on your test as well. All right. Maybe homework, test, quizzes. Okay. Everywhere. The units. The units of the rate constants are very important. I'm going to go back to my notebook to show you something. Here we go. Okay. So I'm going to use a different page. Okay. So please make sure that you understand this very clearly. All right. Because I'm going to test you on this. Okay. So we have, this is very simple, but we need to understand 0th, first, and second. Okay. We know for 0th order, rate is equal to rate constant. Right. And the first order, rate is equal to rate constant time reactant concentration. And then for second, rate is equal to rate constant time reactant concentration to the power of 2. All right. Now let's try to determine the units for the rate constants. Okay. So rate is always concentration per unit time. Okay. So let's call it, let's say the time is in seconds and concentration is in molar. So rate units should be molar per second. Okay. Molar per second. Molar per second. Okay. Sometimes it can be minutes per minute, per year, per hour. It can be anything, but I'm going to assume that it's in per seconds now, per unit time. Okay. Therefore, the units of rate constant for 0th order must be molar per second. Okay, it's pretty straightforward. But when it comes to rate constant for the first order, we have molar for reactant concentration here. This molar cancels out with each other in the rate and in the molar. As a result of that, we see that rate constant is going to have units of per second. Okay. Units. I'm deriving the units now. Okay. Units of rate constant. Rate constant. Okay. And then when it comes to the second order reactions, okay, we have K times molar squared because we have concentration squared. That means the molar must be squared. As a result of that, only one of these M's will cancel out. Therefore, my K will have units of per molar per second. Okay. So this is how we determine the rate constants for 0th, first, and second. They're always like this. All right. So you just need to pay attention to what time units you have. In this case, I assumed I have my time in seconds. Sometimes time is in seconds, sometimes minutes, hours, years, months. Okay. You get the point. All right. Any questions, concerns, comments? Liv, how's it going? Huh? All right. So the slope of the graph was this.
Yeah.
Okay. So for first order graphs, the rate constant
Because that's
is
the only true one.
negative slope,
It's not about like what's the best.
okay,
like,
which is equal to
the other ones don't.
0.0693,
values.
and the units for first order is per unit time. Therefore, this should be per year. This is it.
We're using all three of these and figuring out which ones.
All right. Now, I don't know why we took so long. They're asking, like, the concentration at 10 years. So here's the value. Done.
So technically, like the concentration
Right?
and equals e to the. Yeah. so
That's
you got-
it. Anyway. Yeah, I'm going to come to that. So, all right. No, concentration is not ln. Concentration is that. That's correct. Yeah. All right. So here's the thing though. Okay. Now, I did not mean to be like this. Okay. I wanted, it to be, beyond this time frame or something like that, at least. Okay. So that means we should be able to calculate the concentration at any time point. Okay. I mean, at this point. So how do we do it? Now, let's think about this. I'm going to clear my doodling first over here. Okay. But you already did that. Some of you already did that. Okay. So anyway, so we know for the first order reaction, Ln reactant concentration at time t is equal to negative kT plus natural log of initial concentration. This is it. Okay. And we know Ln at 10 years is what they are asking. That should be equal to negative. And then the rate constant was 0.0693 per year. And the time was 10 years plus natural log of R naught, which is 1 millimolar, natural log of 1, right, which is 0. Right? Therefore, this value should be equal to natural log of, this should be equal to minus, years cancel out, minus 0.693. And therefore, the concentration at 10 years should be equal to e to the power of, so I'm getting rid of Ln. How do we do it? How do we do that? We take the, we take this to the power of e, right? And both sides. And when we do that, we're going to get e to the power of minus 0.693, which is equal to 0.5. Okay, so 0.5 millimolar is your answer. Right? That's the way you do it. I mean, if your time is not within that time frame given. All right. Again, I mean, this is not chemistry now. It's basically, using the equation. All right. What questions, concerns, comments do we have at the moment? Anything? All right. So we'll do some of these, some more of these in a second. But for now, I want to. Okay. We are there. All right. Reopen that. Let's do this. 5, 4,
Okay.
3, 2, and 1. It's already 140. Anyway, it's okay.
Last time we found first order reaction, we
All right.
Ln of A.
So the most popular answer is 37.1. This is what again? The time.
Negative KT.
All right. Let's see what's
If you
going
just
on.
Divide both sides by negative K and get T by.
So.
And just plug in your values. Yeah.
So I plotted the 3 graphs. Okay. So here's the way I approach this. Okay. So it's really mechanistic at this point. Okay. I plotted the three graphs. I plotted concentration versus time. Is the one. The linear regression of R squared was 0.9. Okay. I'm looking at, I'm looking for the one that closest to one. R squared closest to one. Okay, that's what I'm looking for. So zeroth order cannot be your answer because R squared is pretty low. And for natural log of concentration versus time is R squared is equal to 1. That is the best we can get. And then when it comes to 1 over concentration versus time, okay, the R squared was 0.9584. So it's not that closer to 1 as before. So therefore, I'm going to go with this, okay? Now, some of you, I know that some of you might have a misconception. R squared value is your order of the reaction. No, you cannot be further from the truth, okay? R squared value just tells you which graph is more linear. Closer you are to 1, that's the most linear graph. Jacob? No, so but you need the rate constant, right? So you can directly plot ln concentration versus time. You don't have to do the other ones if the question tells you if it is first order. Yeah, but I did that anyway because it's easier to do that. Okay, I have to have concentration anyway. 1 over concentration I plotted because I didn't have anything else to do while you're working on it. Anyway, so now this is our graph. And then we have the rate constant value. I'm going to write it somewhere so that I can use it later. So rate constant should be negative slope. Slope is negative 0.0619. Therefore, rate constant must be 0.0619. What are the units of time here? Is it seconds? Anybody from the table? Okay, let's assume it's seconds. I don't know. I mean, it's not given, right? Let's assume it's seconds per seconds. All right. Anyway, so this is my rate constant. Now I got that. Then I go to my notebook. Okay. Then I, start working away, right? So we know for the linear, okay, the integrated rate law for first order is natural log of concentration is equal to negative KT plus ln initial concentration, right? Therefore, KT is equal to ln initial concentration minus ln concentration at time t, right? Or this is equal to natural log of initial concentration divided by the concentration at time t. It's the same thing. Okay, you can do either way. Anyway, therefore, T must be equal to ln R naught divided by R at time t. Okay, divide this entire thing by rate constant. That's it. Okay, and then we plug and chug. Natural log R naught is initial concentration was, where was it? I'm gonna get that value. At time 0, it is 0.063, 0.0063, or 0.063, right? Okay, it should be 0.063, right? At time t, that's what they're asking for, right? It's 0.0063. It's 0.0063. And divide this by the rate constant, which is this. I know you don't see what I'm writing, okay? I just wrote these values, and at time, at rate constant is 0.0619. 0.0619. Okay, this should be in per seconds. All right. Now, if you do this calculation, it should be, I don't know, ln of 10 divided by, I think, ln of 10 divided by 0.0619 per seconds. Okay, what do you get? Anybody? Can somebody do this and let me know? 37.1. Okay, so if you do that, you're gonna get 37.1 as your answer. That's how we got that value. All right.